Max, also to you, a very good morning, and really nice to have you with us. I think most of the people know Max, so I don't really have to introduce you. Just maybe one sentence, and then we get started with our in-depth conversation. If you want one sentence introduction.
I'm going to say a sentence about myself.
Yeah,
right. Okay. Yes. So very nice to be here. Thank you very much for inviting me. It's a huge pleasure to be here. I've done like a million introductions to investors, actually. So I'll spare you the long version. But I'm basically a theoretical physicist including my PhD. I worked on quantum gravity, but that wasn't going to change the world, and so I changed to machine learning. This was a very unassuming field, actually, at that point. It was like we were talking about models with 10 to 100 parameters. So now we're in a trillion range, so that's truly exponential scaling for you. And so I've been in the machine learning faculty, basically in California and Canada and UK. And 2013, I came back to the Netherlands. Also in the Faculty of Machine Learning. But then I already started a startup at that point. The startup got acquired by Qualcomm. And so I then started to slowly shift towards industry. And so I worked for Qualcomm, who started their research institute in Amsterdam after the acquisition for 4 years. But wireless wasn't really my thing. And at that point, basically, AI4Science started to pick up, and I wanted to do a startup, but then I got a phone call from Chris Bishop from Microsoft Research, who were starting their lab in AI4Science in Amsterdam, and I couldn't say no to that, and then I did that for 2 years, but the itch of a startup was too strong, and it needed to be scratched, and so about, I would say 19 months ago now, we officially founded CuspAI, which is AI4Science, but more precisely AI4Materials. But I guess we will be talking about that more.
Exactly. I tend to be a very structured person, at least that's what my colleagues say. So what we've done is we divided the conversation into 4 parts. And why so? Because it needs to have flow, but also because we want you to actually ask questions. So the first block is very much going to be about, okay, where do we stand? This pivotal journey that Max has briefly talked about, but also a bit the big picture. Afterwards, we go a bit more into what Cusp is doing, a bit more into AI4Science and the different potentials. A third part is going to be more about entrepreneurship, so building a startup in that field, deep tech in Europe, etc. And then the last is more of an outlook of what's going to be happening in the future, so that you get a bit of an overview. And we'll actually do one question after each block. I'll be walking around with the microphone, and every time you get to ask a question, maybe also quickly present yourself and say what you're working on, and then your question, so you can already think a bit what you would definitely also like to include and contribute to today's discussion. All right, let's start. I mean, you've briefly talked about the foundational shift that you've done. First, very much working on graph neural networks, and then also on the VAEs. Looking back, what was for you the most pivotal idea that truly convinced you AI can now move from the digital space over to the true physical world, and especially what you're currently working on, everything related to the fundamental laws of physics, but then ultimately material discovery?
Yeah, so I actually remember this very vividly, which was, I was working at Qualcomm, so in the lab, I have been developing together with Taco Cohen and other people, Maurice Weiler, we have been developing these equivariant neural networks, which basically are a way to tell the neural network about the symmetries of the world. Otherwise, it has to learn all of that from scratch. And so you basically tell it, if you rotate the image, then, and you do a segmentation of the image, then you want the segmentation to rotate as well. And it doesn't understand that if you just train a neural network on data. And so then I got to know about molecules and machine learning force fields that actually have started to build in this equivariance into their force fields. And I thought, okay, that's beautiful because this is an actual example where the symmetry is almost perfect. Maybe if you ignore gravity for a moment, the symmetry is actually perfect, meaning that if I take a molecule and I shift it, or I take a molecule and I rotate it, for instance, the ground state energy will stay the same, and the forces will rotate alongside the rotation of the molecule. And so that connected back to my roots, which was theoretical physics. And I thought, okay, that's very beautiful because I've sort of worked on this machine learning tool, which is the equivariance and the symmetries, and now it's starting to actually do real good in chemistry, because I think machine learning force fields you could probably think of as the most successful way in which machine learning has been incorporated in physics or in chemistry. And I think it still is. And if I want to make a prediction about a future Nobel Prize in chemistry, probably machine learning force field at some point will also, could be one Nobel Prize in the future. And so that was for me the time when I thought, okay, so now I can go back to my science roots. I think science is incredibly exciting. You're discovering the world rather than inventing new things. You're just actually trying to figure out how the world works. And so that's what I thought, okay, I should go back to that and think about machine learning for science.
Fast forward to today. I mean, you're the co-founder and CTO of CuspAI, a company in material discovery, as we mentioned. But what I find super cool is that the materials that you are discovering are in the area of carbon capture. And CUSP is ultimately like a whole platform. So I think what I would be curious to hear from you is if you can maybe, in simplified terms, very briefly give us an overview on the platform that you're building from a technical perspective.
Right. So in fact, the platform is more general than just sorbent materials for carbon capture, but this was the first application area that we looked at. And this is an internal project called Skyvolt that we internally funded as well, to try to find a new sorbent for carbon capture. But we also work on fuel cells, and we work on sort of removing PFAS from water. But all of these projects do have a certain sort of sustainability angle to it. And now about the platform. So in the platform, it's evolving as well. But it's basically, you can think of it as, the easiest way to think of it is as a search engine, where you literally type like the type of material and the properties of that material that you're interested in some kind of query box, known as a prompt these days, or you just type the prompt. And then there is a sort of a machine, sort of a search engine or an optimization engine that starts to run in the background. It's around an agent. Of course, these days everything is agentic, so we are on that train too. We have an agent that will coordinate the search and the computations. So the first thing this agent could decide to do is to say, let's generate a whole bunch of candidates. Actually, that's not the first thing it will do. The first thing it will do is, let's look for data. Is it in our data hold? Is it on the internet? Is it in structured databases, publicly available structured databases? And if it's not, then it might decide to generate new data. And so we will spin off a whole bunch of DFT calculations. It's actually developed here in Berlin by Felix Musil and team, which is an active learning loop that will then go generate only those data points which are necessary for building up that database. And then we'll train machine learning models, or more accurately, we'll fine-tune our models for that database. So let's say we do electrolytes, we try to improve electrolytes for batteries. We'll then create a database relevant for that material class, and we'll start to train our machine learning models. And so then the next thing it could do is, let's generate new electrolytes that we think could improve the current material. So this is a generative model. It's the same model that you use to generate video images or images, basically. But then it will actually generate molecules or materials. After it's done that, it will, the next thing it could do is to say, well, I've generated 1,000 new materials. Are these actually physically relevant materials? Are they actually even physically possible? And so you will have a whole slew of detectors, which would quickly find out whether these things satisfy the basic laws of physics, whether they're charged or not, or whether they have enough volume in terms of a carbon capture, whether they have enough volume to actually capture the carbon. All of these things, whether they, if you put them under a little bit of temperature, whether they will collapse or not. Okay, so we have all these properties, and then we escalate these computations up the chain. So the cheap ones are the property predictors, and then we get more expensive, so we're starting to do MD simulations and MC simulations to compute more sophisticated properties. And then work by Nick and Jonas here in the front row becomes very important, because some of these calculations, for instance for carbon capture, have to do with computing how well does a CO2 molecule stick to the inside of one of these sorbents, and you have to simulate this with an MC engine, and sort of that's very slow, could take up to a day or days on a computer, very expensive, and so they have then accelerated that and put it on a GPU. And then you go up the scale. So at some point you also will need to have an actual a digital twin model, let's say for an actual carbon capture machine, where you put the material in. And if you keep on going, you get to techno-economic considerations. If we actually make this, could you actually make a reasonable sort of a rig out of it that you can actually make money on, or that people will actually start using, all the way up to life cycle analysis.
Mm-hmm. Yeah, and we'll talk a bit more about this inventing molecules part in the second part. But maybe to zoom out before we get to our first question of today, if we talk about AI4Science, and you said that you love science, I do too. You know a bit more about it than I do. So that's why I ask you the question. If we look at the AI4Science part and its societal and economic opportunity that it offers us, what are you most excited about, in a sense that you believe AI4Science can solve that and no other, or if we don't have it, it would not be solved?
Yeah, so there's a couple of obvious answers to that. One is chips is a clear one. Of course, chips are made of all sorts of materials which are layered on top of each other. Of course, semiconductor is the most important one. We run kind of into the wall of the quantum wall, where we are already etching at the level that is so small that it's like almost the size of a few atoms. And so we need to also improve the materials there. The second one that's obvious is the energy transition, which is batteries, but carbon capture, climate change, like removing carbon dioxide from the atmosphere. But there's many more, like filtering toxic materials out of our water supply. There's many of those which have to do with environmental challenges. But I would want to go further and say that basically at the root of almost everything is materials. And so if you want to, at some point you'll hit this materials challenge almost always. I mean, even car manufacturing, everything that has to do with manufacturing will use a ton of materials, and all of these materials can actually be improved. So it's a very fundamental thing to say, well, what if we could actually create materials on demand? You just tell me what you need, and I'll create that material for you.
Sounds like a wonderful vision. All right, first question. Whose hand is up first? Yes. 1 second, I'll hand you the microphone.
Thank you. I'm Sarthak, and I work with Nomad. And I'm wondering, like, when you are training your foundation models or you're fine-tuning them for a particular application, the data that you're getting, how satisfied are you with the data that you get? And is it enough? Or, yeah, if you could comment on your current experience, or what are your expectations for how the data should be improved?
Right, so the data comes in two flavors, more or less, or actually many, but let's put it in two classes. The first one is, or actually three, right? One is publicly available data, like Nomad is an example. There's Materials Project, there's all sorts of databases out there. It's way too little, that's absolutely true, and chemists have the habit of only sort of publishing the successful kind of experiments and computations, and we should get into the habit of actually saving everything, which for machine learning is really very useful. So the second one are the ones that you generate yourself. And of course, you're in the driver's seat here, so you can definitely say, I want this one, I want this one, I want this one. So they're high quality but expensive. And then there is running experiments, the ones that you generate yourself. We haven't actually generated a whole ton of them. A few at the end of the Skyvault project. That was very slow to actually synthesize these materials. We want to go through high throughput. So I don't have a ton of experience of how high quality that is. But the one thing I can say, we always want more and better data. So we are very hungry because we're nowhere near the LLM kind of models of OpenAI and Anthropic and Mistral. I should put in a European one too. So and Mistral, where in fact the data is abundant. And we're always looking for more and higher quality data. So Nomad is really important initiative.
Yeah, I mean, directly want to connect to your question, talking about data, also the geometry of it, and basically that needs to be 3D. So can you talk a bit more about that, in a sense that why do you believe that building that geometry into the model is so important, and how you have approached that, or how you are approaching it at CUSP?
So, the data, it comes in many flavors. So if you do it in your computer, it's automatically 3D because it's a bunch of atom positions and their types. And then you do a whole bunch of computations on them. So then you typically take these 3D positions and you map them through an embedding. This could be the force field, for instance. And then from there, you can do all sorts of property predictions. But you also do MD simulations, you do DFT calculations, let's say to compute the ground state energy. So that for the computational data, it's automatically 3D, but maybe you mean whether the representation is equivariant or not. So these force fields are equivariant, and that's important prior knowledge you're putting into it. But it's important because you make your life easier to predict the properties after a while. So I don't think it's that key, by the way. It's like, it's nice. And because we don't have enough data, it's good to put in your priors and your inductive biases. But I don't think it's like, if we wouldn't have equivariant models, it would be the end of the world. We could still do good science and build the platform.
Before, when we talked about the platform that you're building, we had the different stages that you explained. And I think one stage was very much, of course, about you want to have novel materials in the chemical space, but it's all about also making sure that they're physically valid. I think that you mentioned and that they're stable, and that they're ultimately synthesizable in the lab. So can you go there a bit more in detail, how you also handle this sometimes even like conflict or that line between the two?
Yeah, so I think it's a very good question because one of the biggest challenges is to predict synthesizability. So there's all sorts of kind of computations you can do to make sure that, let's say, it has a low energy so that it's a stable thing that you're creating. But maybe to give one example of something that we encountered and we may not have anticipated is we were generating metal organic frameworks using a generative model, and they all looked pretty on the screen. But then we found that if you shake them a little bit, many of them collapse. And you can actually simulate this in your computer, which is very interesting. And so we actually built a tool which is called floppy MOF. And the floppy MOF detector basically took a MOF and it would shake it a little bit and then would say, would it collapse, yes or no? And so you'll find yourself implementing all of these checks. So it becomes a whole zoo of checks, actually, that you're implementing. But that's at that level, the level of synthesizability, and even like beyond that, like predicting whether something can actually be synthesized at scale, is something that is very hard to predict. And so that is, we try to predict from the literature. Let's see, people have published a lot about these things, but it's like, there is this story that maybe is good to tell about somebody was trying to make a MOF in one lab and then published it, and somebody in another lab tried to replicate it. and it couldn't get it. And then the person from the lab that created it and went to the other lab and said, let me show you how to do it. And it couldn't do it there either, right? And then they had to go back to the lab where it was actually created and do it exactly the same way. And then it happened again, so they could synthesize it. And the reason was the atmospheric composition was a bit different. Like, this is how sensitive these things are, and this is how, yeah, it's kind of a magic art, it really is. And it's hard to figure this out from literature, right? And so you find yourself having all sorts of surrogates for that, and then pray. Now, there is another way around this, which is what we're currently going after, which is instead of computing for a long time and then at the end of it see if you can synthesize it, you know, invert that. Basically, synthesize a lot of things, because if you synthesize it, you have made it, right? And then you can figure out what did I actually make, and can I measure the properties? And that's going much more to the high throughput and self-driving labs space, and Dunya's here, of course, in this space. And so, but I think the real interesting thing happens when you connect the computations with the lab. And this is not just Bayesian optimization, which probably many people know, which is, okay, look at my previous measurements and think hard about what the next measurement is, because that's all, you don't have to understand anything about what's going on in the black box to do that. But if you can actually do computations like simulations and AI accelerated simulations and use that to make a prediction of what the next best experiment is, then you can iterate much faster through your experiment design. I think that's what the future is.
Before we get to the next question, one last question that's more connected to research. I mean, you spent so many years in connecting physics to machine learning, and you've before said that ultimately your mission and vision is to solve everything on the material level. If we now zoom in on the different research areas, what do you believe is mostly overlooked, and maybe connected to that, what has recently been a research paper that you were a big fan of and that everybody in the room should actually be reading?
That's a complicated one. I think what has been most overlooked? Well, I think, first of all, this field is actually quite small. It's just maybe a year or so that is really starting to grow. And sort of, if you go and talk to companies out there, most of them are not, they're not even simulating things, and let alone using AI to accelerate the simulation. So I think the chemistry space is very far behind on what's currently being developed. And I think that's the one thing I think sort of the community at large, the industry, has been overlooking this, and I think this will change rapidly. Now, in my field, I think I have been constantly surprised by LLMs, and I constantly question myself. I'm kind of, it's very strange. I'm in a sort of bimodal sort of state where I switch between one day I'm like super impressed and I think, my God, this is like unbelievable. And then the other day I think, no, it's not unbelievable. It's all crap, right? It's not actually very smart. And this is, for us, is really important, because the question comes, can you actually have an LLM that can is smart enough to steer the entire platform to do the right thing? And they're very smart, so this is a tool using agents, so it gets to use, okay, let me use this tool, let me use this tool, let me do that. But of course, an LLM cannot actually, doesn't have a very strong sense of numbers, for instance. And so it will have to use a tool, I have to understand to use a tool in order to get those numbers. And it's just very hard for me to get, and this may be because I'm old, I don't know, but maybe I'm just actually too old for this, but whether an LLM just trained out of Anthropic would understand how to string together, be smart enough to read what these tools are, to then get a reward, like this is what you need to achieve, and then be smarter than, let's say, a Bayesian optimizer to solve this problem. And so I cannot imagine that's the case, but we are building them, and I'm super happy to be pleasantly surprised. But I think in the end we need to optimize them and fine-tune them ourselves with machine learning again. So that to me, the biggest surprise is constantly being surprised by LLMs, more or less.
I think that's a very good end for now. The next question. You were up very fast, so I'll hand the microphone over to you.
Thank you. Hi, I'm Nikola from Rubik's Code. So I'm interested, like exactly at the last sentence that you mentioned, like you cannot imagine that LLM is actually doing that. Would you think that maybe a smaller model or something more specific to this kind of thing than just slapping on an LLM on it would work? Or
I think there's no doubt something that's being trained to solve the task would work, in my view, right? So it's like, if you go through the problem many times and you tell it, this was good, and it was good because in the beginning you did this, which is classical reinforcement learning, right? You have a whole string of things, like a whole lot of actions you take, and then at the end of this list, you basically say, that was really good. And then it has to figure out, okay, which of these actions contributed to this being good rather than this to being possibly not good, right? And I believe reinforcement learning can definitely do it, but it's very expensive because you have to go through many, many of these kind of runs, and it's super expensive. So the big question is, and so a small model that's being trained using RL would do something good, I'm pretty sure. Whether an untrained LLM would have enough intelligence just out of the box to do it, I think is the real big question. Whether they, somehow it has to be incredibly smart to figure out, here's an entirely new situation, here's all the tools I have. I just read what they can do. This is what I need to achieve, and then do the right thing. If we reach that, I'm once again very impressed. I've been impressed before, like when the LLMs came out and when AlphaGo happened, so I'm very cautious because I don't want to be that guy that constantly doesn't believe in it and then it happens, right? So it's
Yeah, we do one second question from the colleague in the back.
Hello, and thank you. I'm Juan, I'm data engineer, and my question is related to the evolution of, in this case, like a molecule or a compound. And for example, there is this paper from Google where it's this AI co-scientist.
Can you speak up a bit?
AI co-scientist,
Yeah.
where you get a hypothesis and it evolves this hypothesis,
Yeah.
which seems to fall good in this category of evolving a physical property or some property, desired property, to get to an outcome. And it seems that there's also some opportunity to figure out what is the best approach in how to get this prompt that a user would input and then evolve it to an output that is actually materially buildable. And I just want to get your take on how you're trying to tackle and solve this bottleneck of evolving some properties of some compounds, of some proteins, or whatever it is that the LLM is using to reach its conclusion.
I'm trying to see if I truly understand your question, but so you mentioned kind of the AI scientist, which is this tool that proposes hypothesis. All right, so that's a tool that reads the literature and comes up with ideas. I think that's that exists, and that's definitely good to use. You talked about prompt engineering. It is surprisingly important. And in fact, Jonas could tell you some really funny stories about how important that is, but also how you can get one of these LLMs on their knees and have start to behave really weird. And so the actual prompt is really important. So it almost looks like it's in a psychological state. Like you can bring these LLMs in sort of almost like humans in a psychological state in which they will behave differently. And you talked about evolving, but I'm not sure, are you talking about evolving, like evolution evolving, or?
For example, this AI co-scientist has some cyclical steps that it goes through.
Yeah.
Get a hypothesis, rank them.
Yes.
And based on the ranking
Yeah, that's what we do too. So that's exactly the same way that our platform works as well. So, you generate candidates, you read the literature, generate candidates, then you evaluate the candidates. From that, you then generate so you learn, and then you generate new candidates, and you go through that cycle. And so that's the paradigm that basically everybody is following. And that's also what our platform is doing, yeah.
Awesome. In the next part, we like to talk a bit more from lab to market and ultimately building a startup in this very important field. So zooming in a bit on the biggest hurdle, I mean, you talked a lot about work in the lab and getting to experimentations in the lab. But what do you believe is the biggest hurdle from moving something in silico over to really a real-world synthesis and also testing?
I think the biggest hurdle, there's two hurdles we find ourselves in front of. It's not so much the science, but it is synthesizability, scaling, and predicting the things that come later. So it's in other words, can you actually manufacture this material at scale? But possibly even more important, who can you convince to actually use it and sell it, so actually, and pay for it, right? And so the actual field is quite conservative, chemistry, maybe pharma not so much anymore. I think they've kind of moved already into the AI age. The chemistry companies are actually quite conservative, and they work with very small margins, so they have very little money for research. But I think it needs to be cracked open, and once they're going and they see the benefit, they will all want in it. So I think the biggest hurdle definitely is finding the right customers and figuring out how to predict, to synthesize, and integrate the material into actual things that people make out there.
We're here in Europe, and I think we like being in Europe. Ultimately, it's about pushing and taking actions and not waiting. But ultimately, what do you advise to your teams, to young researchers that you see out there, or possibly also clients, that they need to do in order to stay competitive? So what do you believe needs to be taken into action for us to make big step forwards in Europe?
Right, so the biggest issue, so that's first on a positive note. I think Europe is very good. There's a lot of good talent in Europe, and it's quite easy to do a startup, to start a startup. And I guess this building is an example of how government tries to help researchers to take the step from the research lab to the sort of to the startup phase. I think we're pretty good at that in Europe at this point. What we're not so good at is then the scaling part that comes after. And our investors tell us you need to go to the US to scale, and that's the standard story, right? If you play, with sort of investors and you get a lot of investment, and so we did get quite a bit of investment. The next step is you need to move to the US, and this is every company startup will tell you that. And so why is that? Of course, they know what they're saying, but it's also sad because we got. The talent comes from here, the investment from the governments come from here, and then the company moves to the US and grows there. And so the benefits are reaped in the US. So it's a very sad story in some sense. So what we really need to think about, how do we make it easy for companies here to scale? And there's a couple of things, just give you an example. So recently we were trying to negotiate a contract between a lab in Denmark. And our lawyer is a UK lawyer who knows UK law. And so then the battle is the contract under UK law or is it under, Denmark law? And because, you cannot have a lawyer in your startup that knows about law, all of European law. So why is there not one set of laws for startups, for instance, right? So this is one friction point, but there's many more friction points. Like you need to, I think it's true, but correct me if I'm wrong. If you go to Germany and you want to do business with a large German corporation, you need to have a company here, a subsidiary here in the UK. So we have now, We have a lab here, but this is also like for a startup in another country to build a company here first in order to do business in Germany is like too much, right? It's very and so what we need to do is we need to completely homogenize Europe so that a startup can as easily do business in Greece as it can do in its home country.
Yeah, I think that's where then the taxes as an income source for different governments probably intervene, and sometimes also interest conflict. But of course, I very much agree with you. Maybe one question to end this part is a bit, I mean, there's a lot of people in the room that are still relatively early in their career, and I think most of you have finished their studies, but I would still curious to hear from you if you were to start your studies again, or also give advice to young people. Do you think they should start as physicists and then learn ML and potentially transfer into ML, or become a computer scientist first and then learn chemistry? Or how would you, what is the right order?
So things are changing very rapidly. So the first thing you need to be able to do is switch quickly. So you need to learn yourself to switch quickly and adapt quickly, and don't dig a very deep hole around like one topic. But if there's one thing I would say is like, do the hardest thing first, because when you're young, you know, you have the patience to go through, you know, all the derivations. So do math first. I think that's the hardest thing. Maybe quantum mechanics next. Right? To go through all the things which are the hardest. Make sure you know that you'll learn a huge amount of them. And strangely, I mean, computer science is actually also a lot of math, so that part is definitely good to know. But machine learning, strangely, isn't mathematically all that hard. And so you can quite easily pick it up, I think, with a background in mathematics or in physics. You will have to, you know, spend time and do it. But yeah, I would do the hardest things first.
Mm-hmm. Do we have another question? Yes. Let me quickly walk over.
Hi, thank you so much. My name is Ola. I'm interested. So you mentioned that scientific community is pretty conservative in terms of adopting AI, and we see it all over. So what do you think? What would be your way to address it? What do you think we can do to convince them that they should use AI?
Yeah, this is what I'm trying every day. I think the one thing, the one thing is to show success, more or less, right? And so I guess we have plenty of success right now in the AI space. But of course, the story goes much further, much earlier. People were already screaming, you know, AI is coming. It will determine our future economy. Please start working with it now. Now I think we need more amazing, you know, breakthroughs. So one thing for us is we really need the first AI designed material. We don't actually have a fully AI designed material. And so that would be a success to maybe show around. It takes time. And I think the next thing, which is probably good, to make the threshold lower for people to enter, which means good online courses for people to follow. Availability of compute, so the AI factories are probably good in Europe, so give access to GPUs. But possibly also, you know, if we have role models and we have success stories of people that are, I don't know, started a startup and got very successful, I think that will also attract a lot of talent into this space.
Talking about success, I mean, failure is also very much connected to success, because from failure comes success. Can you maybe give us an example, if you like, about challenging moments for you in your research, or also moments where things have failed and what you've learned out of them, and where maybe also things then converted into a step closer to success, or some successful achievements?
I think what I always say is that it's not about failing, it's about how quickly can you recover from failing. So it's like everybody fails all the time, right? That's just fine, but you need to have this learning sort of mindset. Like if failing is a unique place where you can learn a lot at that point, because you have a very good negative data point that can accelerate you. So if you get, if that means you're walking away from it, I think you've really failed. But if you stand up, and keep going, it's like a kid almost. Like if you learn a kid to bike, the kid will fall all the time from the bike on the floor, but it will be very quick on the bike again and try again and try again and try again. I've competed with my children at some point on trying to ride a unicycle, and just observed how more quickly they would learn than I did. And it's like it's very, very quick. At some point I said, I'm just going to go back, and they would just keep on going and keep on going and keep on going until they got it. I have one example of. So I don't think in Cusp, actually, strangely, nothing has totally failed yet. So I think that we hired at some point the wrong people, maybe, that you could call that failing. But definitely on the scientific side, I think there wasn't anything that was completely misconceived. But in my lab, I did have one example, and I actually talked about it in this workshop called Why Did It Not Work Better, or something. That's a workshop in NeurIPS. I wanted a way to sort of compute uncertainty in a prediction by basically coming up with some scheme where I would have like an interval, and then I would do all the computations, and the intervals would sort of, there's a sort of computation on the interval, so that at the end the interval would actually represent the full uncertainty. And it would be perfect because it would actually, you would be guaranteed the answer would be in this interval. But of course what happened is the interval would be unreasonably large, basically everything, and there was no way to control it. And the thing was that, when do you stop? That's the real problem, right? So when do you admit, okay, this was a bad idea? And I think that's an art in itself that you need to master, because it could be the student that sort of isn't good enough, and you think, it's a good idea, I should keep going, right? But the art of stopping in time is something that we all need to learn.
Listening to you now, I think I know the answer already, but I'm still curious to hear it. If we think about materials or AI in materials, do you think we should invent new materials or optimize existing ones, and why so?
It's actually a surprisingly deep question, I think. But if you were to force me to give one answer, I would say definitely invent, and this is what you predict.
That was my guess, yeah.
Yeah. That's what our platform does. It's not just searching through existing materials to find the best one. It's actually inventing new ones, and that's of course where all the excitement is. But I think if you think about what creativity really is, I think it is combining existing small modules in surprisingly new ways, and I think that's also in optimization, if you wish. And I think that's what our platform in some ways also doing. It's using the laws of physics and putting putting atoms together in surprising ways, but still making sure the laws of physics are maintained, are satisfied, to come up with new materials with desired properties.
All right. I'm in the process of getting up again. Do we have any other question? Yes, I'm now coming a bit towards the back.
Hi, my name is Ferdinand, machine learning engineer, also former physicist. But this question is more about the ecosystem as a whole and Cusp space in it. I know this field's growing a bit, and there's Cusp and Danya and whatever in the room, and I know OpenAI. There's some people from OpenAI who've made a spin-off now called Perplexity, I believe. But what do you think Cusp?
Periodic.
Sorry. What do you think Cusp's special positioning within this ecosystem is, and what makes you different from the other players?
Oh, you sound like an investor. This is exactly the question I get from. I mean, undoubtedly, it's a race. And I don't want to claim, we have a magic sauce, except for our team, I would say. But, it's not necessarily that it cannot be reproduced. Other people can also not build very great teams, right? So I think we have a good culture. I think one of the things which is, let me just maybe bridge to a slightly different question, which is, I think what does it take to build a successful company? I think having a good culture in your company is critically important, so that people feel happy going to work, feel excited to solve real problems that are meaningful. I think that's really important. The other really important part is data. So if you have a lot of data, you have a certain moat that is hard to, replicate, because it just takes money and energy to actually generate that data. Working on the right problems, so choosing smartly about what you're working on, having a certain agility, so to pivot easily, which means like you cannot figure out everything from the beginning. It's just impossible. You just have to constantly question yourself, was this the right decision, or should we do something else, right? And so having this kind of agility to say, okay, this was actually maybe not optimal, we should shift a little bit to the right or to the left. That kind of mindset is super important. The other thing is your founding team is incredibly important. Having a very large founding team. We've seen a few examples actually recently in Europe where companies fell apart because the founders, I don't know, they couldn't agree among themselves, or had too big egos, or egos actually also a good thing. So don't have a huge ego is probably also a good. But I don't know what happened there precisely, but having a founding team that gels is really important. So there's all these kind of things that are truly important. And in the end, I think none of these things is impossible to replicate in another team. It just has to come together, all of it. I mean, building this platform is actually quite hard. Putting it all together and making sure the whole thing works is quite difficult. I think we have a good head start, but it is, in the end, like in the LLM space, is going to be a race.
One more question? Okay.
Hi, Jill from Mission to Mars. When you're recruiting engineers, AI engineers, what's your advice? What's your go-to process to evaluate, the best, to find not only to find, but to evaluate the best people, within all the applicants, especially when you're a young startup and you have to, find tech people who work both on data engineering, ML, software development, for example.
Yeah, so we do have basically a process where they're evaluated for their technical skills, of course, right? And so they need to have the right technical skills. But we also have cultural interviews, so the people also need to fit into the company. Now, exactly how, what we're looking for, I know you probably want to talk to Jonas and Nick here, who've done more of the actual interviews precisely on the technical level. But I guess you're either an engineer and a deep belief that AI is going to change science and an interest in learning about science, or you are a chemist or a material science with a strong interest in AI and believe that AI will transform your field, and a willingness to learn about AI. So that's kind of the way, and everybody needs to sign up for this mission that, this company wants to work on things that, move the world forward, not backward.
Okay, one more question.
Hello, this is Moin from Apple. So one question about the science in general, solving with AI. So when thinking about your framework platform, you're having a bunch of problems, like from search, retrieval, the first step, and then generation and the verification. The generalization part of the second part, generation, is usually the problem when it comes for science. For example, for math, we know that when it comes to a completely new sort of problem, like AIME, the using the samples for training a model to generalize this completely unseen scenario is very difficult. How do you find this problem easy or difficult for your scope problem? Because that's basically the key problem we have in LM space. It cannot really generalize well to structures beyond what we've seen before. We've seen for graphs, like graphs or things like that. And the verification is also another problem we have, which is, it looks very easy, but in general, learnability of, for example, prime is a very easy problem to think of, but because of symmetry it has, it's very hard to learn. So learnability is an issue. So how do you find these two problems, generalization of the second step and the learnability of the verification step, the last part, is challenge from machine learning perspective?
So I think the verification part is maybe much easier for physics because we just know the laws of physics, and we know they need to satisfy, there's certain rules that they need to satisfy. So you can build a whole bunch of these detectors basically that tell you whether what you've done so far at least makes physical sense. You can then start to simulate things. We know how to simulate physics. It's a bit expensive, but we can simulate it. We can accelerate this with machine learning tools. And so all of these kind of this evaluation stack is something that the physicists and chemists have been building for decades, right? So it exists. The only thing we are doing more or less is accelerating it with AI. So I think that part is, besides a lot of work, is kind of straightforward in a way, unless you get to very complex systems, like if you go all the way up to an entire battery or something like this, it becomes much more complicated. But even there, people have built models like digital twins. So it's pretty good science. So the generative part, there's a lot of developments, like Google had Genome, Microsoft had MetterGen, we have our own models. So they work quite well, and then the question, of course, becomes how far do they generalize, how far do they expand out of the known area? And I would think of this more or less as the further you go away, the more likely you break physics, and so the harder it gets to, do something that's actually correct. And so I think you just need to think of it as you can guide these generative models in a certain direction. So you first have a model that's built on known data, so it probably just interpolates between things that are known. And then you push it towards the fringe where, where you may not have seen a lot of data. And then you keep verifying that this is actually correct. This is not correct, this is correct, this is not correct, this is your filter. That creates valuable new data, and then you can retrain your generative models in this area. And so you work your way towards the material that you're interested in. It's not magic in the sense you can just generate anything out there, right? That model doesn't exist. The other thing is you can put a lot of inductive bias in it. So one of our first models that generates metal organic frameworks just generates the components and puts them in approximate positions. And then there's other tools like a MD simulator or like an energy minimization tool that will then put things in place in a way. So there's a huge amount of inductive bias because the code that would generate the actual three-dimensional instantiation of the molecule is just a completely deterministic piece of code that was written with a lot of physics knowledge.
Thank you so much for that last question. Then we do the last question from you.
Hi, my name is Olga, and I'm not in science, but I'm looking for scientists. I will talk about that later. My question is, do you have success that you developed material that did not exist, or you improved existing materials? Because it seems like the startup exists already for a while. Like, do you collaborate with certain companies that need those materials, and you help them improve the quality? Like, what is success that you already have?
Yeah, so we're 19 months old. So, but I think it's fair to say that we have seen in the field a material which is completely generated and successful out there by an AI system. Although there's some claims left and right, and so we are mostly on the path of, let's say, improving a metal organic framework for carbon capture. But we can't claim a massive success for that. And so I think the easiest things you will see is like small improvements to existing materials or improved formulations, like mixtures of things that are like better paint or better coatings or something like that. That's probably the first successes you'll see, and there's probably already AI in that. But an entirely, so for instance, a new high temperature superconductor or these kinds of things, they're nowhere near to be developed by an AI, also should say maybe, I never say that in these days, but maybe, you know, I don't think right now we are there. But I do think we'll soon see success, let's say, in a better electrolyte in a battery or something like that. So those are things that I think you could definitely improve with AI. But yeah, maybe the answer is, at this point, I don't think there's anything 100% developed by AI that is a sort of breakthrough material.
Yeah, I was most asking about your company. What do you consider success of your work?
Well, okay, so I would say success for us is we do work with, the other part of your question is, do we work with companies? Yes, we definitely work with a whole bunch of companies. Success is if a company would actually take our design and produce it at scale and put it into their products. Then I think you have reached success. You know, you can do lots. Publishing a paper about something is nice, will educate the rest of the world, but it's for our company not considered success. So for success, if we actually start to sell a particular material and it makes it into the real world.
Max, thanks so much for all your insights, and thanks so much to you for being here. We now still have cake left. There's also croissants that are still here. I believe also coffee. So please stick around and talk to not only the person right and left from you. Here in the first row, we have Nick and Jonas and of course Max from CUSP. There is Alex here from Dunya if you have questions. And there's Charlie sitting all the way in the back from Cambridge. So if you want to talk to some of those representatives, please do. If you have any Merantix or AI campus related questions, you know where to also reach me. Thanks so much, and see you next time.